Hey guys, how are you? I hope you're really fine. Today in this video we are going to talk about how to design calculation of time embedded drive. This is going to be an example with some experience that I had some years ago about a system on a CCW power generated plant. It is something like this. Maybe you don't know it, you can search it. This is a presentation that I did in the days, but don't worry that we are gonna make it again. Everything. I'm gonna explain you. The objective of this was to demonstrate that the current belt is an optimal for the system. The problem is because the maintenance check, we just we could hear a lot of noise. We could see the how the real condition, the wearing condition of the belt was. So for that situation, there was a lot of decisions. And so in the project area, decided to talk with two different manufacturers, and that one of them decided to put a drive pulley of 37 millimeters width, and the other was just try to continue. I'm hiding those names because I don't wanna say that information, but well, for that, actually, the result it was possible to check that our dimension of the belt that we have was the correct for the system, but we also verified that it was the basic task, like this, the standard for lower quality and short useful life. And today, there's more options. So if you can buy it a little bit expensive, but it's gonna save you money in maintenance and more, so it's okay. This conclusion I recommend. Well, this is the result of all the calculation that we are gonna see. And well, we are gonna demonstrate why this idea of that quotation that they said us couldn't work. Okay, first, if you don't know what kind of the system we are talking about, this is the system. As you can see, there's a motor in vertical position. This is gonna be a drive pulley and a driving also with the blades. I have a little bit here. It's like this. Maybe. Okay, you have the motor, the drive pulley, the belt. I mean, yeah, and the driving pulley and the blade. There's a small blade, but this is the idea. And also, where it is there? Okay, it's vibe. We're gonna use the OptiBelt technical manual for timing belt drives. As you can see, you can just download it on his page. And there's a video I'm gonna show you. Is the motor, the position of the vertical motor. That is the technician, the blades, and here the driving pulley. As you can see, it's not something small like this. It's a little bit bigger. No, it's a little bit big. Well, we decided also to, and this is the drive pulley. And see, this is the real drive pulley. There was a maintenance check. We also, I remember we also changed the bearings of the motor and something like that. But this is just to show you how this was. So we are gonna calculate some of here things. I'm gonna show you how it works, each part by part, and well, just we have to pay attention. First, we need to know this is the real data that I have in the drawings of the or in the data sheet, or you can see in the case of the motor, you can go to the you, you can go to the system and check. The RPM of the motor is 1775 RPM. The radio, well, you have two different options like RPM, you have the number of teeth, or diameter, but I remember that I have that information because this is my because I have the drawings. I have the drawings here is about the system. So, well, this is just a small part of the drawing because I remember that I had more data, but that's how I could have the radio. So this is for real data. If you don't know, you just when the system is not operating, just go and try to have an approximate to distance. And then this is just that we should start. You're gonna need the basic load factor that it's in. We're gonna check this. This is 0, and we have this table. The total factor is gonna be the plus of all these factors, but that basic load factor is this. And as you can see, you have different options. There's only one mistake because it's twice up to 16 hours. One is up and the other is over. So just check it. It's not the end of the world. So the situation that we have is an electric motor. It's not a mid-set in reality, but it's kind of that. It's an eccentric drive. So we have to mix or try to, yes, to match this. We are this in an electric motor because this you can see how in the case that you are in the low type of the, that's example for you. And as you can see, you have here eccentric drive. So this is you just match this and this, and you have 1.9. So we in our case, basic load factor is 1.9. Then the speed radio correction factor, I think is the next page. As you can see, yes, here we have the speed correction. It depends on the radio, but as you remember, we have 7, and here we just have only 1. So if you have more than 1, just put the maximum that you have, 0. So simple. In the case of fatigue correction factor, oh yes, here we are in an operating time. Oh yes, sorry, I didn't mention it. Here, that's gonna be depend of the operation or working operation of your job or the plant. I don't know that you're gonna be in my case was here, but maybe for you it's here. That's gonna change, yes, but just to remember it. So as you can see, we are here. So it's a continuous operating. We were here 0.2. Because the overall factor is just plus these three loads, the total load factor maybe. The motor power, this is the data of the motor, so you should know it in this case. Remember that we are gonna demonstrate why the different manufacturer option didn't work. So, but we are also gonna select it. The design motor power or design power, you just multiply the total factor and the motor power. So then after this, you should go diagram of belt profile. Yes, as you can see. This you're gonna have three, if I remember, HL, I think it's the best quality. Here you have more. And as you can see, you have the HP quality, and then you have the fan power that is special for this. It's special for just the system we have. So we should just match this. As you can see, we have 93.95. So we are just here, the design power, as you can see, and match with 1070. Okay, like here. Here was a problem. Oh no, not a problem, just a decision. I have a picture here. Yes, as you can see, we are here. Oh, sorry. And we could decide for a HM or a 14M profile. So what bulb should be selected? In this case, you could select HM too also, but or maybe you should be very detailed with your selection. But something that in this situation that we have is that we have a lot of noise. In the last maintenance, we have a lot of noise and a lot of wear on the teeth of the belt. So something that we consider is to have more height for this, and is that as you can see, for HM profile we just have here 5.4, and in the case of 14 we have 9.5. So this is gonna depends on the it is gonna change also then the drive pulley, but we have the best engage of the transmission. So that's the reason why we decide for 14 profile. So for here we have for sorry, this is in Spanish because I have to. Okay, I have the video in Spanish also. 14 HP or uh, fan power. Okay. And then we have to have a recommendation about the diameter of the drive pulley twice the diameter of the shaft of the electric motor. In the case this is a real data 60, but as you remembered, in the case I put here, if I'm gonna show you here, we can see the different drive pulley diameter that it sits on the for its commercial. I think okay here like here. Uh, I think it's here. Yes, 14. This is the profile. You can search the profile. The width. Just wait a little bit. Don't worry about it. And you have these different diameters. The sub W for the case for this case. So you just check it. Okay? The minimum is we have 120. So you should okay the next one we should go for 124.78. Yes, could be, but in this case I put the real data because as you remember we know the real drive pulley. So this is something uh, that I did on that moment on the plant. Uh, and for if I remember, this was this. It was 32 teeth with 142.6. So this is 142.6. Number 32. So then we have the number of the driving pulley. You just multiply with the radio. But if you want the standard of the driving pulley, you should check it. And you can see you have 224, and the reason to the maximum is 216. You should put 216 because it's that. Okay. And then well, you have go to the commercial or the standard diameter that we have here. It's you can see 9,062.57. 9,062 point. Okay, if I yeah. Okay. And the driving speed we also know it's in the it's just with This is a simple relation that you can see. Then you have the drive center distance. This is by A drive center distance, but if in this case there's a recommendation from the optimal range that this you're gonna start to manage this. But in this case, well, as you can see, I have the drawings, so that's how a complete drawing is not here, but I have this data. So I'm gonna just put the real value because if I remembered. Sorry if you don't know, you can use uh this 0.5 with this five these two diameters. Oh, here, yes. You maybe use guys put the half of this of the plus maybe. But if you don't know the drive centralism in this case, for me was I have some data here. Uh, okay, this was sorry. Okay, then the optimal range. There's something here that doesn't work. Oh yeah, it's here because it's with a point. Okay, so it's an Excel. The theoretically, theoretically, maybe belt length. You can just calculate since that equation with this equation. This is with Spanish nomenclature, but if you don't know, this L is the belt length. C in this case is A. The drive center distance, when is the same C, and the diameters of the pulleys. Okay, so with that we just should change. Then we with that now you did that theoretically belt length. Now you should go with what is the standard belt length. So we are with a 14 belt, 5 belt. So you should go and search it. Everything's here. So maybe 3M 5 here. This is the 14 profile, and you can see we are here 3,760. So there's no the next one 3,850. So 850 millimeters. So now you have the real or the standard bell length. So now you should calculate uh, C in this case of A, and I put a paper or maybe this is the roots of quadratical equation. So just put it. I've the value also, but you can just search it. Just have to calculate C in this case. L is gonna be 3,850 on the different diameters that you have here. So now you should just calculate C or A. It's the same. And then I'm gonna move on. Yes. Number of teeth in the mesh of the small pulley. This is how many teeth uh, are engaged of the transmission. So this question is for here. Also, C norm is the C standard or A standard here. I'm gonna put maybe C norm equal A standard. Okay. Just for here, the next one. Well, no. Is theoretically. And you should just calculate. It's this equation. Number of of teeth of the dry poly divided in teeth. It's multiplied 3 minus the relation of the difference in the polyamers and the drive center distance. So then you have here, as you can see, we have with decimals. Just go to the next one. Oh no, sorry. Here, let's go to the next one because we have 11.5. The next one is 12. It's 11.3, 11. Um, so using the mesh factor, this is a table C1. We are gonna search it. Here we are here number of teeth in the mesh of teeth. We have 12, so it's higher. So we are here. The mesh factor C1 is 1. We should put 1. Belt length factor C7. This is also here. We are in a profile for team M, and we have 3,085. No, 85. No, 3,850. So we are here. So we should put 1.1 for C7. 1.1. The optimal range of power you're gonna see. Of, if I remember, it's here. Yes, here. All right. Okay, here. This is page 49. This you have much here because you remember that you have the nominal RPM. You have 1,775. So we are here, and our small pulley is number of teeth is 32. This is our we select. So we should match here. I have here and here. Yes. And we are in the middle, so we should interpolate this. You interpolation just this, and then you're gonna have well now right now I have the value just to make the video uh, a little bit shorter, and it's here 53,465. Okay, as you can see, this is the result of the interpolation. We are here, and this is the value. Then the belt width. Well, this is something that we should track. Uh, there's a condition of the every design here that your transient power of standard belt width should be higher than your design powered. Designed, design powered. So the width is okay. If the width is okay with your different power, the transient power with the design power, so it's okay that your design. What can I find? Where can I find this? It's here. I think it's here. Yes, with correction factor. Well, you have the standard belt width. Standard. So it's commercial. You have 40, 55, 85. So you have this 5 and this factor. So I'm just gonna put different 85 because this was the actual of that drive pulley. But maybe how do you know it? No, don't worry. If I don't know it, don't worry. Don't worry. You can just it's because the width section factor is gonna difference you 2.5. 2.5. This width section factor is gonna change it. If I change this, no, don't worry. It don't affect anything. This is how you if you don't know if you don't you should tabulate. As you can see, I have a small here. This is the design power that we have here in the beginning. This we have different width of the belt width difference, the three, and the transmission. So how do you know? Well, because I changed this width section factor. I put now 2.5, put 1, 1.44, and 2.5 to calculate this with all this. You should multiply all these factors to have it, and that's how I have this number, because now it is just the same. Yes, and if you can see, less than 93, less than 93, and it's higher than 93, so it's okay. The reason why I minimum it's 85. So with this, as you can see, Luis, with this information, now you only with this you can see, you can check that the option of the different manufacturer is not the best. Yes, it's true. It's not the best because it's not gonna work. It's not gonna work. So as you can see, we have this is the belt that we need. This is the option that we showed you. But if you want more information that we have here, so I really wanna check more, because I really want to know if how torque we need to move all the blades, and if we can know the real shaft diameter of the driving shaft. I'm going to show you how. First of all, we calculate the minimum adjustment of the standard of a standard. You should multiply the equation, multiply with the real center distance, or the standard center distance by the reality. Then belt speed, as you can see, this is if you have in meters per second. You have the diameter and your RPM. It's a equation that we have if you have. Then this circumferential force to be transmitted. Well, this is the equation. I put be careful with the units. You have the speed and the motor power, and if this is not more the as you can see, this is the symbol, maybe, if you can say that, but this is not more that force. It's force like this. It's force. Circumferential force. It's like power equal force multiplied with speed. It's just a question. So you are calculating the centrifugal force. Now more. Okay. Then we have the test force. This is something that we use in the predictive maintenance. Maybe if you don't want to know how many forces you should prove the belt, you can calculate this. Just the equation is divided by 20. Also, the drive span length. This is the equation of this. I'm gonna show you just to, if you can see that I've not invented anything. Sorry. Um, here, okay. Here you have this question here. As you can see, I'm just showing how to using this information for your success. This is the we are drive span length. Yeah, we are here. This is the drive span length, the real standard center distance, uh, and with your Cooley diameters we have. And then you to calculate the belt deflection, you should divide that span length by 50. So as you can see, I just put that and divide it. Then I have the belt deflection. Then for the minimum static shaft force, this is the equation. You should multiply your circumferential force 1.1. It's also here. I've not invented anything. something that something that it's already exists. If you wanna demonstrate how wide, well, it is for another video. I'm just show you how to use the information that already knows. The bulb width, well, it's also how to the bulb width you should have. It is depending on the top profile, and as you can see, for each 10 millimeters bulb width, you're gonna have this value in kilogram per meter. So I just multiply 85 in this case, divided by 10 and multiply 0.1 because it's here. Maybe it's for different profile, different numbers. The frequency is also the equation with that information that we have here. The equation, because in an Excel something it's really could be hard. And as you can see from here, you have well 0.5 multiplied with your minimum static shaft loading and divided 4 by belt weight, your belt span length per meter. So it's also here. And now you can know the drive pulley torque and the driving pulley torque. This is just your transmission powered with your your motor RPM, the first, and for the driving you use the second speed, the driving speed. Okay, remember that we calculate this with the radio. So no more, there's no more. So with this information, I just copy this with just to have it. If you, as you can see, the driving torque is higher with 85 with pulley and belt, and its benefit, as you can see, it's not maybe here in the graphic it's short, but in reality it's a complete system. The technician is here, man. If you can see, it's not the blades, the weight of the blades, so it's a lot. So also to check and confirm more this, as you can see, the problem just finished. But I would like to check because I remember that I calculate the diameter of this shaft. This is for shaft calculation, but well maybe the condition of how it's working is torsion. The material it's C45. This material it's you can search it on table. It is a DIM norm. Just search it here. Here you can this. Uh, you can check this norm in like DIN and 083 and the sorry. Here. Okay, this is how you can see the bonified steel for this material and the pulse and shear stress in millimeter twice. I remember 340. As you can see, driving torque. This is the same data we have here. Just check the maximum safety factor. This is a DIM norm also. It's 5. This is the maximum of and how you calculate the diameter. Well, as you remember, this is for shaft calculation. Maybe that's for another video, but let's check it. The shear stress, your shear stress divided in the safety factor. Uh, it could be your shear. No, yes, maybe here. Sorry. Uh, yeah, your pull shear stress dividing the safety factor is gonna give you the shear stress. But also remember that this works only with the condition when you just note when you have the power and the speed of the in this case of the pulley. This is for different topics maybe, but and when it's this safety factor is was only you work in torsion. If with flexion, with deflection and torsion, it's different safety factor, but in this case, it's just torsion. So your pulse shear stress divided in the safety factor, and that's equal. Remember, if you remember about your resistant materials class of the university, maybe I don't know, 16 times your torque momentum. I'm not really sure if this units it for English, but I'm trying to put it. Your torque momentum divided by P multiplied cubed of the diameter. So you just put that equation, and I have the diameter of the shaft. Oh, it's in Spanish. Sorry, this is 75.25, and the reality of that, if you check the drawings, we have this. This is the real data. So that also checked that everything was okay. This is the reverse engineer that we made, but this only was to check. So as you can see, we could demonstrate how well these two different manufacturers just was checking for their, maybe I don't know, economy, maybe I don't know, but this option definitely, and this was the great option for the system. And I put it not possible because the transmission power is not greater than the design power. This is the principle, and also the torque different, a lot of torque. We lose here twice, so we should check it. So the only condition that we recommend is to just to not buy the standard, buy the fan power if in the manufacturer, in the market exceeds something special for this, that guarantee you a high shear stress, low frictional coefficient, as you can see, low noise, long service life. So please buy it. You're gonna reduce some maintenance intervention, something like that. Okay. And with this, another is that I'm just I'm just wanna remember you that always believe in your theoretically experience also that you learn here. As you can see, well, this is in Spanish, sorry, but as you can see, if you don't know something, do it, practice. They have this Excel, but it's not the best. I know that today there's a lot of Excel with a lot of picture, maybe, but this is the most simple that I use it for my job, and I did it. As you can see, just numbers and numbers, but it works. It works. So do it. Do your Excel by your own to understand and to practice this. This is the best option. I know that now you can just say, hey, could you give me the Excel? Now it's easier, but maybe you are not learning anything. You just are learning how to put the boundaries, but it's gonna help you. At the end of the day, in what moment in your job, it's gonna help you a lot. Um, Another that always remember that there's no reason, because different manufacturers come here and have different proposals, but you also have to check. It's your job to check if that quotation that they have to you, their option, is the best for you. You should always ask you why by yourself, why they have this option, just to check it. And I remember a technician also checked, hey, but we can use the V belt, maybe, no the timing belt, the V belt. But yes, we check, like as you can see in the last video, we check the same situation and we demonstrate that we need a drive fully of a lot of groups, so that it's not in the market. So, but it's okay. The technician could have his opinion, and it's okay. You should work together. It's okay because you need it. So never be how can I say it? Don't be afraid to fail. Maybe it's okay. Maybe they could fail here. Yes, could be, but don't worry. It is totally normal for each one of us. It's totally normal. So you just check and recheck your numbers. Well, that I hope you really like this video. But if you have questions, please just do it. I'm gonna try to load more videos about different topics like conveyor, how to design a conveyor system, or your centrifugal pump, how to select it, dimension it, your turbines maybe also. So for renewable energy, maintaining different manufacturers, bearings, how to calculate tribology and lubrication. So there's a lot of topics that we can talk then. So just check it. Well, have a nice day, guys.